There's a planet 77 million kilometers from here that scientists have been trying to explain for decades. And they can't. Not because they lack data, but because the data they have doesn't fit any model we've ever built. It has the largest iron core in the solar system relative to its size. It has ice on the planet closest to the sun. And it has a geological history suggesting that something enormous, something catastrophic, completely transformed it billions of years ago. Today, we're going to tear it all apart. What you think you know about Mercury is wrong. And by the end of this video, I'm going to tell you something almost no documentary ever mentions. Something the Messenger mission found in its final months, just before it crashed into the surface at 14,000 kilometers per hour. Stay with me. Mercury, the first planet in our solar system, the closest to the sun, and probably the most misunderstood of all. Most people dismiss it. It's small, it's hostile, no moons, no rings, no real atmosphere. But here's the problem. The more we study it, the more questions appear. It has the most disproportionate iron core in the entire solar system. It has ice at its poles, despite surface temperatures hitting 430 degrees Celsius. And it has a geological history, suggesting that what we see today isn't what it always was. Something happened to it, something massive, and we still don't know exactly what. Today we're going through it all. What science has found in the last 20 years, what the Messenger mission discovered up close, and what BepiColombo might reveal before 2030. By the end of this video, I'm going to tell you something almost no documentary mentions. Something that could change how we understand the formation of our entire solar system. Let's start with the basics, because even the basics with Mercury are surprising. Mercury is the smallest planet in the solar system. Diameter, 4,879 kilometers. To put that in perspective, it's smaller than Ganymede, Jupiter's moon, smaller than Titan, Saturn's moon. There are moons of other planets that outsize it, and yet, it's a planet. It takes 88 Earth days to orbit the sun. Fast. Makes sense. The sun's gravity pulls it along furiously. But here's the first thing almost no one mentions. It takes 59 Earth days to rotate on its own axis. That means its day is longer than its year. Wait, that's not even the strange part. The combination of its orbital speed and its rotation creates what physicists call a 3-to-2 resonance. For every 2 complete orbits around the sun, Mercury rotates exactly 3 times on its axis. And what does that mean for someone standing on the surface? The sun rises, stops, moves backward, stops again, then continues forward. The sun moves in reverse across Mercury's sky. Let me say that again. The sun goes backwards on Mercury. This was so confusing that astronomers assumed for decades that Mercury always showed the same face to the sun, like the moon does with Earth. They were completely wrong. It wasn't until 1965, with radar observations from Earth, that astronomer Gordon Pettengill proved Mercury was rotating. In that strange resonance nobody had predicted. 20 years of wrong textbooks. 20 years. And that's just the beginning. Because when we start talking about Mercury's interior, things get genuinely weird. Now we get to what scientists call the Mercury problem, the core. In a normal planet, the internal structure follows a pattern: outer crust, mantle, and at the center, an iron-nickel core. On Earth, that core represents about 17% of the planet's total volume. On Mercury, the core represents between 55 and 60% of total volume. Think of an orange. Normally, the peel and pulp are most of it. On Mercury, almost everything is seed. Why? We don't know for certain. The leading theory is dramatic. About 4 billion years ago, Mercury was a larger planet, a thicker crust, a more developed mantle, something closer, in some ways, to Earth. Then something hit it, an object the size of a small planet, a brutal, catastrophic collision. The energy was enough to literally strip Mercury's outer mantle away. The outer layers were blasted into space. What remained was the core, with very little on top. It's exactly what's believed to have happened to Earth when the moon formed, a giant impact that ejected material. Except in Mercury's case, that material didn't form a moon. It dispersed. It was lost. But here's the detail nobody talks about. If Mercury lost its mantle in that impact, where did that material go? Could some of that iron and silicate have ended up in Venus? In Earth? Computer simulation models suggest yes. That part of the material composing Earth's mantle could have originated in that ancient, larger Mercury that no longer exists. We may carry Mercury's fingerprint inside us. Then there's the magnetic field. A planet Mercury's size, with that composition, as cold as it is today, should not have a magnetic field. Models predict its core should be solidified, no movement, no dynamo, and yet Mercury has a magnetic field, small, weak, tilted relative to its rotation axis. But it's there. How? We still don't fully know. What we do know is that this magnetic field is so asymmetric that it's significantly stronger in the northern hemisphere than the southern. And that asymmetry, no model predicted was possible in a planet this small. Drop that in the comments if you knew this, because it still stops me cold every time. Mercury has ice. Yes, ice, frozen water, on the planet closest to the sun. Before your brain collapses, let me explain. Mercury has an axial tilt of just 0.03 degrees, essentially zero. That means its poles always point perpendicular to the sun. No seasons. No variation in illumination angle throughout the year. The floors of craters at the poles have never, not once, been hit by direct sunlight. Never. In those permanently shadowed floors, temperatures drop to minus 180 degrees Celsius, 180 below zero, on the same planet where the sunlit surface hits 430 degrees positive. A difference of over 600 degrees between different points on the same planet. And in those permanent shadow zones, there's frozen water. This was first suspected in 1991, when radar telescopes from Earth detected unusually bright reflections at Mercury's poles, the kind of reflection ice produces. Definitive confirmation came in 2012, when the Messenger probe captured the first direct images of those craters. What it found exceeded every estimate. Not thin ice films, not residual traces, up to 100 meters of ice depth in some North Pole craters. The total amount of frozen water at Mercury's poles is estimated in the hundreds of billions of tons. But there's something else in those polar craters. Messenger detected not just ice, it detected organic matter, complex carbon compounds mixed with the ice. Not life, let's be clear, but the chemical building blocks from which life could emerge under different conditions. Organic matter, on Mercury, 57 million kilometers from the sun. Starting to see why this planet breaks every rule? And the thing almost no documentary mentions is still coming. Hold on. There's a region on Mercury called the Caloris Basin, Caloris, from the Latin heat, and the name fits. It's the hottest region on the planet when facing the sun, and it's the largest scar in Mercury's history. The Caloris Basin is 1,550 kilometers in diameter. Picture a crater covering all of Western Europe, from Lisbon to Warsaw. It formed roughly 3.9 billion years ago during what astronomers call the Late Heavy Bombardment, a period when a rain of asteroids and comets hammered all the inner planets. The object that created Caloris was enormous. Estimates suggest an asteroid between 100 and 150 kilometers across. The impact released energy equivalent to trillions of nuclear bombs. But the truly astonishing thing about Caloris isn't the crater itself. It's what's on the exact opposite side of the planet. When that asteroid hit Mercury, seismic waves traveled through the entire planet, through the core, through the mantle. And when they reached the point directly opposite the impact, they all arrived at once. The result was a region of completely shattered terrain, chaotic hills, irregular cliffs, a landscape that looks like someone shook it from below. Geologists call it the chaotic terrain, or informally, the weird terrain. It is literally the point where the shock waves of Mercury's greatest impact converged from the other side of the world, like firing a bullet through one end of an apple and having the other end explode. And inside Caloris itself, there are mountains, concentric mountain rings reaching up to 3 kilometers high, a full mountain system inside a crater large enough to fit Europe. The heat from the collision reactivated internal volcanism. Lava flowed back into the crater and reshaped it. Caloris isn't just a wound, it's a place where the planet rebuilt itself after the blow. The models didn't predict that either. In October 2018, the European Space Agency and Japan's Space Agency launched a joint mission that could answer many of these questions. Its name is BepiColombo. It will enter Mercury's orbit in 2025, and its instruments are significantly more precise than messengers, capable of imaging surface details down to 10 meters per pixel. 3 major questions BepiColombo has a real chance of answering. What keeps Mercury's core active? Why didn't it solidify? What exactly are the polar deposits made of? What types of organic molecules are there? Is the magnetic field asymmetry stable, or is it changing? Before 2030, we should have answers. But now, the thing I promised you at the beginning, the thing almost no documentary mentions. In Messenger's final months of operation, before it ran out of fuel and crashed into Mercury's surface, its instruments detected something in the surface chemical composition that didn't fit. Certain regions of the northern hemisphere showed significantly higher concentrations of sulfur and carbon than expected. Not in the polar craters, on the open surface. In 2016, mission geologists published a paper suggesting these concentrations could indicate the presence of graphite, crystallized carbon, a layer of graphite buried just beneath Mercury's crust. Where would that graphite have come from? The most accepted hypothesis is extraordinary. In Mercury's earliest days, when the planet was still completely molten, the magma ocean floated carbon at its surface, like residue floating in broth. And when that magma ocean cooled, that carbon was buried just beneath the crust. Mercury may have a graphite layer beneath its feet, a dark crystalline shell lining the interior of the smallest planet in our solar system. And that carbon is the same base element as life on Earth. I don't know if that has direct implications for Mercury's habitability. Probably not, but it seems impossible not to ask. If the carbon is there, if organic molecules are in the poles, if the planet may have had more temperate conditions billions of years ago, what else don't we know? Mercury has been there since the beginning, 4.5 billion years. It survived bombardments, giant impacts, the loss of its mantle, the sun growing hotter, and we still don't fully understand it. The closest planet to the sun, the one that should be easiest to study, the one we visited less than Mars, Jupiter, Saturn, and it turns out to hold more unanswered questions than almost any of them. That says something about what we assume we know. If this video made you think, subscribe, hit the bell, and tell me in the comments which facts surprised you most. Mine is always the graphite. Until the next mission.